Modern AI platforms like Vehixcare ingest an immense volume of data. Every second, millions of data points converge on a single server. This inbound traffic consists of heavy, continuous streams, real-time OBD2 diagnostics, global GPS telemetry, predictive maintenance logs, pouring in from thousands of vehicles. The default architectural approach to handling this is simple. Engineers route all of this heterogeneous data straight into a single application server, which writes directly to a single database instance. That structure holds up perfectly in testing environments. But in production, as concurrent connections cross the 10,000 mark, the physical computing limits of that single machine are breached. The application thread pool exhausts, incoming telemetry packets are dropped, service centers lose connectivity entirely, and the centralized platform halts. High availability requires a cumulative stack of specialized design patterns, each engineered to isolate and manage a specific type of compute load. To scale a system from a failing monolith to one capable of handling 100 million records with 99.999% uptime, we have to rebuild the architecture layer by layer. And that starts right at the front door, with the inbound traffic. We place a load balancer before multiple nodes. Layer 4 balancing inspects the TCP/IP envelope for maximum throughput. But Layer 7 opens the payload, reads headers like telemetry, and routes requests to a specialized cluster for heavy writes. In the .NET ecosystem, this is executed using YARP, or Yet Another Reverse Proxy. Because telemetry streams rely on long-lived connections, a basic round-robin distribution would quickly unbalance the servers. YARP utilizes a least connections algorithm, actively measuring server load and routing new traffic to the node with the most available capacity. It simultaneously performs active health checks against every node. If one server fails to respond, YARP instantly severs traffic to it, routing data to healthy servers. Distributing the application load keeps the servers online, but it simply pushes the structural bottleneck deeper into the internal system. Now, all those healthy application nodes are hammering the exact same database with read operations. Application servers bombarding a single database cause latency to spike. We mitigate this with an L1 in-memory cache inside each node for microsecond access, and a centralized L2 Redis cluster positioned in front of the database for session data. This operates on the cache-aside pattern. When an application needs data, it checks Redis first. If the data isn't there, a cache miss, the application proceeds to query the database directly. It retrieves the record and immediately writes a copy back into the Redis cache. All future requests for that data will hit the L2 cache instead of spinning up the database disk. Implementing this exact pattern reduces direct database load by 85% and drops average response times from 200 milliseconds down to just 15. Caching successfully eliminates the read latency bottleneck, but it does nothing to solve the next major physical limit of the architecture: physically storing and writing a dataset that is rapidly exceeding 100 million telemetry records. This animation illustrates our storage problem. A single database node physically cannot store or effectively write a dataset of this volume. To scale further, the database must split. Database sharding horizontally partitions a massive dataset across multiple servers. If we use range-based sharding, grouping data by dates, all telemetry routes to exactly one server, creating a dangerous hardware hotspot while the other servers sit empty. To prevent this, Vehixcare implements hash-based sharding in MongoDB. It runs an immutable identifier through an algorithm, scrambling the distribution. This ensures every write operation is perfectly and evenly distributed across all available shards simultaneously. The success of this design relies entirely on selecting a shard key with high cardinality, meaning it contains millions of unique possible values to guarantee the data doesn't cluster. Sharding grants us virtually infinite horizontal scaling for storage, but by spreading all this data across multiple physical machines, we drastically multiply the overall surface area for hardware failure. Hardware failure is certain. Each shard expands into a replica set. The primary node handles write operations, asynchronously copying data to two secondary nodes. If the primary fails, the secondaries instantly promote a new primary to resume writes. Replica sets provide performance scaling through read preferences. By utilizing a secondary preferred read strategy, the application routes heavy analytical read queries directly to the duplicate nodes. This preserves the primary node's processing power strictly for high-speed writes. This automated redundancy guarantees 99.999% availability, allowing the system to fully recover from a hardware loss in less than 30 seconds. Replication secures the database layer from localized physical crashes, but the internal system is still highly vulnerable to cascading network failures, originating from external integrations. This animation illustrates the final vulnerability. Our application servers frequently request data from external third-party services. If that external API experiences severe lag or an outage, it stops returning responses. If the application simply waits for standard TCP timeouts on every pending request, those blocked calls will rapidly exhaust the local application thread pool, dragging our perfectly healthy system entirely offline. We implement the circuit breaker pattern. In the closed state, requests flow freely, but consecutive failures are counted. At the threshold, the breaker trips open, instantly blocking requests and returning fallback data to protect the local thread pool. After a timeout period, the breaker enters a half-open state. It lets a single test request through to check if the downstream service has recovered before fully closing the circuit again. Circuit breakers isolate network failures. They transform what would be a catastrophic system-wide freeze into a controlled, localized degradation of service. Looking at this unified system diagram, we can see the fully constructed production-grade architecture that has evolved from our initial failing monolith. These 5 pillars operate simultaneously. The proxy balances the traffic, the multi-tier cache handles the read latency, sharding physically distributes the storage limits, replica sets secure the hardware, and circuit breakers guard the network. But high-level architectural patterns are useless without rigid code-level discipline. Implementing this robustly requires strict adherence to solid principles at the application layer. By heavily separating interfaces and maintaining single responsibilities, engineers can easily swap out a caching layer or upgrade a load balancer without ever having to rewrite the core business logic. This foundation guarantees survival under load. The next challenge is managing how these distributed microservices communicate with each other asynchronously, the exact topic we will tackle in Part 2.